AB Calculus lesson on implicit differentiation. This is the introduction portion of it. Yeah. So do me a huge favor, guys. Try both of these. Okay. The difference between the two is that this is written explicitly in terms of y with respect to x, and this one is written so that y is on the same side as x. So technically, it's not really implicit per se, but just try that out, okay? And then do something similar over here, guys, okay? And then there's a reason why we call it implicit differentiation, but just a note, the only thing that you have to understand is that when you have something like this, when you differentiate it with respect to x, that would be 2y times dy dx. And this over here, you're going to have to use a product rule. Remember that? So this is 6x times the root of the second, which is dy dx. The second, y times the derivative of the first, which is 6x, is 6. All right, guys? All right, guys. Pause the video. Okay, guys. There you go. So when you solve for this, we do ddx of both sides. And ddx of y is just dy dx, right? And then what we have over here is that we're differentiating with respect to individual pieces. I kind of wrote it out, but you really don't have to. So this is like more like, hey, that's what's happening kind of thing. So to make that even clearer, let me actually put a little thought bubble. This is what you should be thinking. You don't have to write that out, okay? And that yields 6x plus 7. Here, we put the y on the same side, didn't we? Right, when you do ddx, this is what we end up with. Same exact answer. Makes no difference whatsoever. So you don't have to solve for x. So we're trying to get your feet wet with an implicit differentiation, but this is what we need to do. Now, if you're thinking, why is that implicit differentiation, Mr. Yin? Well, if you solve for x, right? Sorry, solve for y, you're going to end up with plus or minus the square root. It's going to be or. Right? Yeah, I know. So it's better to do implicit differentiation. And when you did that, and we ended up with differentiation of the x squared is 2x. And that is, as I mentioned before, 2y dy dx. The derivative of the 25 is 0. Solving for dy dx, we get negative x over y. So what does that really mean? Well, if you sort of think about it, right? Let's move this like a little closer. Let's say if you choose 0.11. It doesn't have to be 1, 1, but... okay, why don't we do this? Why don't we choose a point over here that is root 3 over 2 comma half. And then the slope at this point, shouldn't that be perpendicular over here, guys? Right. The slope over here was basically changing y and changing x. So this right there is negative change in x over change in y. Oh, wow. Yes. So this is actually showing that that must be true. So in this particular case, at that point, my slope at root 3 over 2 comma half, as it turns out, it's negative 1/2 over root 3 over 2, which is essentially negative 1 over root 3. Right? There you go, guys. Anyways, let me change color so that it kind of stands out a little bit. Make it green. Okay? All right. So part TB says for textbook, example 2. Anyways, when you do this, differentiate that, that's just 3x squared. And that's just 3y squared dy dx. Using the product rule, I'm just putting 6x as the quote-unquote the first term. And we end up with this right here, guys. We're going to put dy dx on one side, everything else on the other. And when we do that, dy dx turns out this way. Now, in this particular case, right, if you try to solve for y, isolate the y on the one side of the equation, you really couldn't do it, could you? So in those cases, we have to utilize implicit differentiation. And this is what it looks like. So if you want to choose that point, you should get negative 1, right? And then you could say, judging from looking at this picture, you could tell by switching let x equal to y and y equal to x. Let's swap them, see what happens. you end up with the same exact equation. So you knew that this had to be reflexive about y equal to x this way. Okay, guys? All right, so I'm not going to plug in any values, but that's what that is. Okay, now let's move on to the next set of problems. How about this right here? Okay, so here's a note for you guys. Okay, when to use this technique? Well, if the equation is implicitly defined, that is to say, when y is not explicitly solved, cannot be explicitly solved for x, right? And x and y cannot be untangled or mixed up together in the equation. So that's what it means to be an implicit equation. What is my procedure? Treat y as differentiable equation, differentiable variable of x. All right. Take d dx as both sides of the equation. We follow all the rules that we learned so far: quotient rule, product rule, chain rule, all that good jazz. And then what we did was we gathered all the dy dx together and we solved, didn't we? Okay, guys. Why don't you guys go ahead and try these two problems. This one could be found in your textbook. This is a problem that's made up. Okay, why don't you give it a shot? Alright, guys. When you have done so, this is what you should have gotten. So, the derivative of that is cosine of x. The derivative of that is negative sine of y times dy dx. And there's a product over here, right? It's the sine of x times the derivative of that, which is negative sine of y dy dx. And then the second one, that cosine of y times the derivative of that, which is cosine of x. I underline the dy dx. I'm going to put everything on the one side of the equation this way, which we end up with this. We're going to move this one to this side. We end up with this. And what we noticed was that this side, we have cosine of x in common, so we factored that out. As I divide by this over here, I notice that they both have sine of y, so I factored it as I did it, and there you go. That is it, guys. All right. All right. So this over here, if some of you were expanding this out to use sine of x, sine cosine, right? Sine of x cosine of y plus cosine of x sine of y, you are doing two product rule. And then you're going to have to put it back again. So don't do that. This is a u. So the derivative of that is cosine of u times du dx. And we take the derivative of that, that is 1 plus dy dx. Anyways, you distribute this out. I'm putting all the dy dx on this side and cosine of xy on this side. When you do, this is what we get. Right? I just like they're both negative, and I don't like to have negative if I don't have to, so I just swap them. Right? So we negate both sides, solve for it, there you go. Alright, guys? Okay. Alright, so I apologize. I'm trying a new way of recording so that the recording itself is a little shorter, so you don't have to hear me like bumbling through the individual problems with a lot of ums and ahs, right? Anyways, let's take a look. This is your turn. You should do this on your own, and I'll just show you the answer, but I won't walk you through it. If you have issues, we'll talk about it in class. Okay? Why don't you guys go ahead, pause the video. Alright, guys. Here it is. This is what I have, and I'll just zoom in a little bit so you can see what's going on. Alright, you know what? I can't help it. So when you have equation of the tangent line, so that's basically equation of the line, right? So that's y minus y naught equals m times x minus x naught. The word tangent tells you that I'm going to find the slope by taking the derivative of this. That's all we're saying. So because x naught, y naught was given to you, you know what you should do? You should just plug it both 2 and 3 for x, y, just to see if it works. And it does. So the slope is y prime of when it's 2 and 3. I'm expecting when I do the derivative of this to have x and y term mixed in together. So for x value, I got to plug in 2. For the y value, I got to plug in 3. Note this, guys. That is a product rule right there. So that's what I did. To make it go a little faster, I put y prime instead of dy dx. But be careful. I noticed that sometimes you might think of that as a y to the first power. If you think you're going to make that mistake, please don't use this notation. Or at least try to put a little curve there. Okay, that might actually help. But I know that it doesn't have it because when you take the derivative, everything is to the first power, right? Anyways, I combine the y prime terms on the left. I put everything else on the other side. I see that as negative. To get rid of it, I swap these two. Or you could think of it as multiply by negative to both sides, right? And I got this. I plugged in for x for 2 and y is 3. What I did was 7/4. Plug it in. That's what I got. Alright, guys. This one. So this is a little different. Show that the slope is defined everywhere. So I just solve for it. So this one's actually pretty straightforward, right? And then when I did, this is what I got. Now, as soon as I see a fraction, if the denominator is equal to 0, it's undefined. So it's not defined at every point. But is it 0? That's two ways you could show that. Either way is okay with me. One, you could say that cosine of y has to be, oops, my bad. That should have been including -1 and 1. So those are the possible values, right? So it is not possible for it to be 0. In other words, 2 minus minus 1 gives you 3. 2 minus 1 gives you 1. So this, by looking at that, obviously has to be between 1 and 3. Sorry. Yes, 1 and 3. Okay? In the second one, I did the same thing, except I made a boo-boo. So that had to be 1. So I must have thinking the answer first, okay? So what you start with is that cosine of y is -1 and 1. But then again, negative cosine of y also has to be -1 and 1. You add 2 to everything. You end up with the fact that 2 minus cosine of y has to be between 1 and 3. So you got to justify this. So this is really, really important. Now the conclusion. So when you try to show something, you literally have to show what you're thinking, right? You have to show and justify your position. So since the denominator cannot be 0 per either one, because, and you would just fill this in, right? So y prime or slope is defined at every point on the graph of 2y is equal to x squared plus sine squared y. All right, guys. Thank you, and I'll see you tomorrow. Bye-bye.